Hi, it's Element39 again, and welcome back to another video about iron. In this video, we'll be talking about how mankind has been exploring the usage of iron in industry. Due to a quirk of the electrons, the transition metals share electrons from their two outer shells instead of one, the norm for the other elements. This is what makes the transition metals conductive, dense, and durable. However, iron is used so widely today because of its relative abundance as the fifth most common element in the Earth's crust and as the most abundant transition metals. Due to this, the element was used by mankind ever since the Middle Bronze Age, though the displacement of bronze by iron would not be until several centuries later. Much of the iron used in those times would have been sourced from meteorites because of the fact that iron is often in ores and needed the relatively high temperatures of 15,000 degrees Celsius to be smelted, which can only be achieved in the kiln. Because of that, many iron swords and tools were made using a method called cold forging, where the iron is pounded until it assumes the desired shapes with hammers or the like. In many ancient societies around the globe, iron had a value many times the value of gold. Assyrian writings at the time stated that iron was worth 8 times as much as gold, and the pharaoh Tutankhamun was buried with 2 daggers, 1 iron and 1 gold, showing the value placed on iron objects in ancient times. However, due to the ease in which iron corrodes, many ancient iron artifacts have not survived to this day, and ones that have survived are brittle and rusted. It wasn't until the era of the Roman Empire when the practice of blacksmithing and ironworking was developed and refined. While the native Italy had relatively few deposits of iron ore, the expansion of the Roman Empire brought many areas of the world into their hands, as well as the mineral deposits. With the conquest of Britain, Macedonia, and various other countries of the ancient world, the Romans had increased their iron production rates from approximately 0 tons a year to approximately 83,000 tons a year, as well as producing 80,000 tons of lead and 15,000 tons of copper, making them one of the most advanced civilizations at the time. In comparison, Han China, which had a similar population, only managed to produce 5,000 tons. As well as pioneering the use of metals in engineering and weapons, the Romans also developed and mechanized the extraction of iron from the ores, using the knowledge of engineering to make it quicker and more efficient. They used water wheels to power the slowing of stone and had invented tilt hammers, which would crush the ore and was mentioned in many contemporary accounts of the mine, such as from Pliny the Elder, a notable Roman philosopher. There is also surviving evidence of the usage of reverse overshot water wheels to drain mines of their water at the Rio Tinto copper mines in Spain. Iron swords, blades, and armor were donned and used by the military and made the Romans essentially unconquerable. There is also evidence of a sophisticated system used to separate gold, silver, and copper, as the 3 elements would often appear with each other in nature. However, the use of iron in the Roman Empire is also what made it so deadly. There is evidence of the 3 main types of armor made of iron and bronze. Lorica segmenta, the recognizable plate armor that many associate with the Romans. Lorica squamata, an armor with small iron or bronze scales that were flexible and strong. And Lorica hamata, the Roman version of what we would now call chainmail. Various lances, swords, daggers, and spears were made with both iron and bronze, making them deadly and durable at the same time. As a bonus, many Roman iron products had a small layer of steel on their surface as a side effect of the forging process, which prolonged their lifetimes and made the blade edges much thinner. The downfall of the Romans ironically came from the spread of the knowledge about iron and metallurgy in general, leading to their downfall in 476 AD, where the emperor's soldiers mutinied and killed the young emperor's father, ending the Roman Empire for good. Because of pure iron's defects and relative softness, pure elemental iron is not often used in industry today. Instead, the iron is converted to steel, which is harder due to the presence of carbon and other additives. However, this is where it gets complicated. The amount of carbon in the iron determine what it is and its properties. Wrought iron has the lowest ratio of carbon to iron, with less than or equal to 0.08% carbon, leading to its flexibility and use in decoration and ornamental structures, such as statues. However, wrought iron's counterpart, cast iron, has carbon levels anywhere between 2.1% to 4%. The varying levels of carbon in these alloys are what determine their properties. Wrought iron is more flexible and malleable than cast iron and is used for decoration today. On the other hand, cast iron is used in a variety of ways, most notably in cast iron skillets, pans, and pots, favored by chefs because of their superior thermal conductivity and ability to retain the heat. Steel, on the other hand, can have varying amounts of carbon and other additives due to the different types of steel produced today. The most commonly used steel today, low-carbon steel, is normally made with 0.1% carbon or less and up to 0.4% manganese, leading to its high formability. The low-carbon steel is able to undergo plastic deformation to a higher extent than of the other steels. Steel can also be cold forged, although if the carbon content is any higher than 0.5%, it will be too brittle to be worked with. Iron is different to all of the other alloys of iron because of its extremely high carbon content of around 3.5% to 4.5%. Because of this, pig iron is only used as a precursor to steel, wrought, and cast iron. The failure to properly cast and remove the carbon in the iron can cause it to be unsuitable for the purposes it is being used for, especially when people are involved. The Tay Bridge of the Dundee serves a stark reminder of just what can go wrong in engineering and design, and the implications of cost cutting over the safety of the customers. The Industrial Revolution was a time of change. Through the invention of the Newcomen steam engine and the improved design by James Watt, the steam revolution was beginning to take hold. This invention transformed the world, changing how many businesses ran, and powered the first factories as well as transforming transport into the first steam trains that ran on the power of steam. By the late 1800s, the steam train had taken Britain by storm. Now, places that originally took many days of travel by coach could now be traversed in a matter of hours and led to massive volumes of people flocking to the beach in their spare time, escaping the smoggy air of London and the poisonous confines of their homes. The steam train also impacted the environment. In 1840 alone, nearly 2,414 miles of railway were built in Britain. As the Victorian age continued, more and more inventions and discoveries were being made, and engineering grew and expanded as well to accommodate the structural needs of every new train that was travelling across the landscape. The Tay Bridge was one of them, a bridge across the River Tay, a 4-mile-wide river that was part of the Edinburgh to Aberdeen train line that stretched from Dundee to Burnet's Land. Made and designed by Sir Thomas Boach, the bridge itself was deemed safe and travelled over by Queen Victoria herself, who duly awarded a knighthood in recognition of his achievement of building the bridge across the Tay River, making it the longest bridge at the time. The bridge was a new design, one that used the so-called high girders, where the train would travel inside of the rails instead of outside. Trains travelled across this bridge for only 5 months before collapsing and taking the lives of 60 passengers and crew aboard the fateful train. the 28th of December 1874, the train passed over the bridge over stormy waters and winds, causing the already fatigued metal of the bridge to be strained even further. When the train passed over the bridge, it collapsed, killing all that were on it. Subsequent investigations on the bridge revealed that it was doomed to fail. The cast iron was stressed, and the bolts holding the bridge together were too thin. The cost cutting by the foundry in which the iron was sourced in the railway company also contributed to the demise. When the company asked for the best iron produced in the foundry, they were unaware of the unique rating system at the foundry, best being the worst and best being the best. So, they inadvertently bought the lowest quality iron from the foundry to use in the bridge. The official investigation also revealed that the holes in the lugs were conical in shape instead of being cylindrical, putting extra stress on the bridge. All of these factors, plus the stinginess of the railway company, led to the ruin of both the bridge and its engineer, Sir Thomas Booch, professionally ruined, who died a year later after the accident. To this day, there are still many mysteries surrounding the bridge and its collapse, with many still disputing the total death count and what caused its collapse. However, it remains a stark reminder of what can go wrong in the engineering process, especially with bridges. Hi, it's Element39 again, and thank you for watching this video, which is the second part of the iron series. Next time, we'll be talking about fool's gold and the fascinating history and geology behind it. Don't forget to like and subscribe to my channel, and see ya! Bye!